All right, let's dive right in. Today, we're going to build a digital filter right from the ground up. We'll be using one of the most fundamental techniques out there in signal processing, the Fourier series method, to design what's known as a finite impulse response, or FIR filter.
So, here's our game plan. First, we'll get our heads around the absolute basics of FIR filters. Then, we'll kind of daydream a bit about what a perfect filter would look like before we roll up our sleeves and get into the math and the practical steps to actually build one.
First up, the basics. You know, in the world of digital filters, you've got choices. So why would you go out of your way to pick an FIR filter for whatever you're building? Well, an FIR, or finite impulse response filter, pretty much does what it says on the tin. If you send a short burst of signal, an impulse, through it, the filter's reaction is finite. It eventually just settles down completely to zero. Now, this is a huge deal because it guarantees the filter can never become unstable and start spitting out crazy, oscillating signals. This little chart here really lays it all out. FIR filters, like we said, are always stable. But maybe even more important, you can design them with what's called perfect linear phase. And what that really means is that all the different frequencies passing through your filter get delayed by the exact same amount. This prevents all kinds of weird signal distortion, which is absolutely critical for things like high-fidelity audio or super clear medical images. The only real trade-off, they usually need a bit more computational muscle than their cousins, the IIR filters. Now, there are a few ways to tackle a design. For our purposes, we're going to focus on the foundational method, the Fourier series method. And notice that little detail. We're doing it without a windowing technique. Trust me, that's a really important distinction, and we'll see why a little later on. Okay, so before we can build anything, we need a blueprint, right? We need to know what a perfect, absolutely ideal filter would even look like, at least in theory. In a perfect universe, our filter would be a literal brick wall. It would let through every single frequency we want with a gain of exactly 1, and then, bam, instantly block every single frequency we don't want with a gain of 0. A perfectly sharp, instantaneous cutoff. Here's a cool thing about working in the digital domain. Frequency responses are periodic. The response you see from 0 to pi is just a perfect mirror image of the response from pi to 2 pi. This symmetry is really handy because it means we can just focus our analysis on the range from -pi to pi, which usually makes the math a whole lot cleaner. So, how do we take that ideal brick wall blueprint and turn it into something we can actually build and use? The secret sauce is the inverse Fourier transform. The tool we need for this job is the inverse discrete time Fourier transform, or IDDFT. Think of it as our mathematical bridge. It translates our design from the frequency domain, our blueprint, into the time domain. And what it spits out, this h of n, is a set of numbers called the filter coefficients. These numbers are literally what will make our filter work. Now here's the engine that powers the whole process. I know, the integral might look a little intimidating, but the idea behind it is actually pretty straightforward. We're just taking our ideal brick wall response, which is our HD, plugging it into this formula, and adding it all up across all the frequencies. The result is Hn, the specific coefficients that are basically the DNA of our filter. But this leads to a massive practical problem. The impulse response for that perfect brick wall filter turns out to be infinitely long. And since we can't exactly build a filter with infinite memory, we have to make a compromise. We have to cut off or truncate that infinite response. This single act of truncation is the central trade-off of this entire design method. Okay, enough with the theory. Let's make this all really concrete. We're going to walk through an example, designing a simple low-pass filter from scratch. The whole process follows 4 really clear steps. First, we define our ideal frequency response. Second, we fire up the IDFT to calculate those impulse response coefficients, the h of n. Third, we take those coefficients and use them to create the filter's transfer function, which is just the mathematical description of the filter. And finally, we can take that function and actually implement it. So here are our design specs. We want a low-pass filter that lets everything through between -pi/2 and pi/2. And for our compromise, our truncation, we're going to limit the filter to a length of 11 taps. You can just think of taps as coefficients or little memory slots. This gives us a filter order of 10. So we do the math, we solve that integral for our specific low-pass design, and out pops this formula for our coefficients. It's a classic sine of x over x shape, which you might know as a sinc function. This little equation lets us calculate the value for almost every single coefficient in our 11-tap filter. Now, I said almost every tap for a reason. What in the world happens when n is exactly 0? If you plug that into the formula, you get sine of 0 divided by 0, and that is undefined. So how do we figure out the value of our most important coefficient, the one right in the center?
The solution comes from a really neat tool in calculus called L'Hopital's rule. It's designed specifically to handle these weird indeterminate forms, like 0 divided by 0. By applying it and seeing what the function looks like as n gets incredibly close to 0, we find the true value of our central tap, h of 0, is exactly 1/2, or 0.5.
Awesome. We have all our numbers now. It's time for Section 5, actually building the filter. Let's take these coefficients and assemble them into a working transfer function. Now take a look at these calculated coefficients. You should spot a pattern right away. They're perfectly symmetric. h1 is the same as h-1, h3 is the same as h-3, and so on down the line. This symmetry isn't just a happy accident. It's the specific mathematical property that guarantees our filter will have that awesome linear phase we talked about. And this symmetry also makes for a really efficient filter. When we build the transfer function h of z, we can be clever about it and group the coefficients in pairs. See how the terms for z to the -4 and -6 are paired up? They share the exact same coefficient. This structure is exactly how we build a linear phase filter in the real world. Okay, one final thing, and this is super important if you're ever going to actually do this. Our entire design has been in this mathematical world of digital frequency using radians per sample. How do we connect that back to a real-world specification, like a cutoff frequency in hertz? The answer is frequency normalization. It's a simple but absolutely essential step where we convert an analog frequency, like 500 hertz, into the digital frequency in radians that our formulas need to work. And to do that, we need one key piece of information, the system's sampling rate. And this simple formula is the bridge. The digital cutoff, omega sub c, is just 2 pi times the analog cutoff in hertz, all divided by the sampling frequency. So in our example, if you have a 500 hertz cutoff with a 2000 hertz sampling rate, you get exactly pi over 2, which is the exact cutoff we started our design with. See? This is how the math connects directly to a real-world application. So there you have it. We've designed a filter. But let's just stop and think for a second. We built this thing by taking a perfect infinite response and just chopping it off. It's kind of a brute force approach, right? So you have to wonder, what kind of weird little distortions or ripples might that harsh cutoff introduce into our frequency response? And more importantly, could there be a smoother, more elegant way to do it? Well, that sounds like a topic for another time.